How can we evaluate models? So let's see how we can evaluate models for regression and for classification. For regression models, typically we use MSE, which is the mean square error. We prefer models that minimize MSE. Other metrics include root mean square error and mean absolute error. Another metric for regression is the coefficient of determination. It's the measure of the goodness of the regression model, and it is defined as the ratio between the sum of square of the regression divided by the total sum of square. We now talked about model evaluation for classification. The first metric is confusion matrix. We have actual classification on the rows and predicted classification on the columns. There are two classes, class 0 or the negative class, and class 1 as the positive class. In the first cell, we have actual classification as 0 and predicted classification as 0 as well. So this cell counts toward true negatives. In the second cell, the actual classification is 0. However, predicted classification is 1. So this cell counts toward the false positives. In the third cell, the actual classification is 1, but the predicted classification is 0. So this counts toward the misclassification as false negatives. And in the last cell, the actual classification is 1, while the predicted classification is 1 also. So this cell counts toward the true positives. The sum of the columns counts toward the total actual positives. That is for the positive class. And for the negative class, the sum of the columns gives the total actual negatives. Look at the total for the rows. The sum of the true negatives and the sum of the true negatives and false negative give the total predicted negatives. And the sum of false positive and true positives give the total predicted positive. And sum of all the counts in the 4 cells gives the grand total. We now look at an example. In this example, we have 25,000 records. If the income is less than or equal to 50,000, we call this class 0, or the negative class, because this is a class of non-interest. Application or loan applications in this class will be denied the loan. The second class is the for income greater than 50,000. This is class 1. We call this the positive class because this is a class of interest. Loan applications in this class will get a loan. So this is our confusion matrix. We have actual classification on the row and predicted classification on the columns. We have the negative class or class 0, and we have the positive class or class 1. Similarly, we have those classes on the columns. We have the true negative, the false positives, the false negatives, and the true positive. and the sum as well as the grand total. We continue with evaluation measures on this slide. The overall error rate is the sum of the false negative and the false positive divided by the grand total. The overall accuracy is basically just 1 minus the overall error rate that we got previously. The proportion of false positives is the false positive divided by the sum of the false positive and the true positive. And the proportion of false negatives is the false negative divided by the sum of the false negative and the true negatives. Now if we look at the confusion matrix, previously we saw in the previous slide, for the overall error rate, we plug into numbers, we get the overall error rate, which is about 13.5%. And similarly, the proportion of false negatives, we plug in the numbers, and we get about 12.3%. The proportion of false positives, after plugging a number and calculate the ratio, we get the result as about 19.3%. A good classification model should be sensitive, meaning that it should identify a high proportion of the customers who are positive, meaning have a high income. So the sensitivity, which is also called recall, is defined as the true positive divided by the sum of the true positive and the false negative. It is also called the true positive rate. The higher, the better it is. So from the confusion matrix, we plug in the number of true positives divided by the number of actual positive, which is this number, this sum on the right side, on the column on the right side. So we plug those in and we get 57%. A classification model also needs to be specific, meaning that it should identify a high proportion of customers who are negative, meaning have low income. Specificity, also called the true negative rate, is defined as the ratio between the true negative and the sum of the false positive and the true negative. From the confusion matrix, we look for the true negative and also the false positive. The sum of the false positive and the true negative is actually on the column in the right. So we plug those in here and calculate. We get about 95.7%. Next, we talked about precision. Precision is also called positive predictive value, or PPV, and it is defined as the ratio between the true positive and the sum of the true positive and the false positive. From the confusion matrix, we look for the true positive, which is here, as well as the false positive, meaning actual classifications are negative, but misclassified as true, as positive. So we plug those in. The sum of those numbers is actually provided in the last row. So we plug those in here. And then we get this result, which is about 80.7%. For models such as spam classification, false negatives are less of a concern, while false positives are precision is better here. The Fmeasure, or also called F1 or F score, is the harmonic mean of precision and recall, and it is defined as 2 times precision times recall divided by the sum of precision and recall. From the precision and recall previously calculated, we can get the Fmeasure or F score, which is about 66.9%. Another measure is F beta. F beta is a weighted measure of precision and recall. It basically assigns beta times as much weight to recall as to precision. In the case beta is 1, then it is just the same as F1. The next measure is ROC, or receiver operating characteristic curves. It shows the trade-off between the true positive rate or sensitivity on the y-axis and the false positive rate on the x-axis. The area under the curves is measure of the accuracy of the model. So if we look at the area under the curve for ROC equal to 0.9, we have this area. Compared to the area under the curve, which is 0.7 and which is less. So closer to the diagonal line, then the less accurate the model is. Next, we talked about the lift charts. The lift is defined as a proportion of positive hits in a set of models positive classifications divided by the proportions of positive hits in the dataset overall. So first we look and calculate the proportion of positive hits in the set of positive classification. You got the first number, which is the positive hits, and also the second number as the records classified as positive. So plug those in. We get the proportion of positive hits in a set of positive classifications, which is 80.7%. And then we calculate the proportion of positive hits in the dataset as a whole. So we also look at the confidence matrix. We got the first number, and the second number. The second number basically is the grand total, and plug those in, and then we get 23.9%. So from those we can calculate the lift, which is 3.37.